Hi and welcome to part 4 of our Kicad tutorial. Now we're going to actually start connecting up the rest of the circuit here. So this is a circuit, and this is a version of circuit that uses a coin cell battery because that is a bit more appropriate for a Christmas decoration. Unfortunately, even with these 4.7k resistors and each of these drawing 0.4 milliamps, the whole circuit still is drawing about 5 milliamps, which means that on this coin cell battery, you know, if it doesn't get switched off because of the voltage drop over time, it will last 44 hours, you know, and so that's probably not long enough for a Christmas decoration. So you might want to, I don't know, you suppose you could have a few of these on the back in parallel, or you could use AA batteries and then it'd last you a lot longer, like a couple of weeks or something. That's probably appropriate for Christmas. In any case, experiment to that with that to your heart's content. Let's connect up the 555 timer. Now it's powered by VCC, and I'm not going straight from VCC, which in our VCC in our case is 3 volts from the battery. I'm actually going via a resistor to try and reduce because I'm trying to reduce the power footprint as much as possible. So I'm added in a resistor there, W for a wire. I'm going to add P to add a power component. I'm going to add VCC in there. I'm going to connect up VCC to there, and I'm going to give this resistor a value of actually 470 ohms. Now I've just been experimenting really on my board to find these values. So that's why I've chosen 470, because I'm trying to minimize the voltage that it'll operate at. But if the voltage is too low, then either the LEDs won't light up because by the time the voltage is dropped and gets to them, it's not high enough to power them, or even the 5.5 timer won't work or something like that. But it works on this voltage and with 470 ohm resistor. Then what we need to do is so threshold detects when to trigger discharge, and connected to threshold we will have our capacitor. So we actually have to put in the resistors, which are effectively going to charge the capacitor on threshold. Now the first resistor then will go into here, and the way I want to do this is like this. So there we go. So there's effectively a resistor between pin 8 and 7. Then we want another resistor here. No, I don't want to do that. So if I add another resistor, A and then R to rotate. No, wait, let me just drag this out. I'm going to drag this back, because what I want, we want it so that, W for wire, we want it so that any power coming here has to go through both of these resistors. That's really, what we want. The resistor should be between these two pins, not between that and there. So that's it for the resistors. Then what we have on the same bar as the resistor, I'm going to have to drag both of these out actually. We've got, oh no. Oh god. Just let me delete this. Right, cool. So, I don't know why I did that actually. Right, there we go. Now, we're going to put the capacitor between here and ground. So, add a capacitor, C for capacitor, rotate it round, and we're actually going to use a polarized capacitor in our case. So is there a electrolytic capacitor? Yeah, condensateur polarize. Which way is ground? I don't actually know what that symbol means. So because of that, and I'm not going to redo this video, let's just put a non-polarized capacitor in there. But we'll use an electrolytic one when we actually make it. So stick a junction in there, connect up the wire. I couldn't tell what the polarity was supposed to be on the other one. And then we will then add in a ground. So P for power, ground. Oh, by the way, in case you're wondering, if you just press A, ground is actually in there anyway. You don't have to press P. P is just allows you to search through less crap, I guess. Right, so that's most of it, and then this is not connected. We're just not connecting this at all. So there's a symbol here, not connected, and you can just say, nope, that's not connected. And that'll allow the kind of design rule, the electrical check to pass, and it won't complain about that not being connected. So what else have we got here? We have the ground. It has to be connected up, obviously. Then we have trigger is connected to the threshold. We have our output. Just let me drag this, and then we output. What I'm going to do here is create a wire, press L for label, and then call that clock 555 out. So that's our clock, right? And then we have reset. And since we will never want to reset our 555, it's active high, the reset pin. So I will just copy this ground by pressing C and connect that to ground. So we never reset it. Now that is the 555 connected up. Okay, that was wrong. The reset is actually active low. So it would be nice if we knew that was inverted logic, and so we really need to connect that to VCC. So we'll reset when it is pulled to ground. So we want that constantly high so it never resets. I'll tell you what, let's change that then. So if I go back into the library browser, library editor, edit that and put that there, then that will remind us that reset is active high. Save that. Yep. You can see it's immediately changed it. Active low. Alright, cool. So that is now the 555 connected up. What we need to do now is connect up the shift register. Now we know, for example, that one of the first things that happens is we're going to connect this to 555 out. So the 555, our 555 output, no, it doesn't, drives the serial clock pin, it drives the register clock pin. Now the way that the reason it can drive both of them is because they're actually, the register clock will always be one clock period ahead of the serial clock, which means that you can shift in a new bit before it then displays those new bits. Otherwise it'd be very difficult. You wouldn't be able to, you'd have to control those pins independently. Okay, so we know that this output enable, this needs to go to ground because we want to enable the output and then it's inverted. VCC there, power VCC, P for VCC. That out. Then what else have we got here? It's SR clear. It's again a kind of reverse logic pin. So to clear it, we pull it to ground, and we don't want to pull it to ground, so we want this permanently pulled up to VCC, so that we do not clear the like the whole state of the system. So that's most of the pins. Oh, and there's an actual ground over here, so let's just copy that. And then the rest of the pins, we have Q prime, which is the output after QH when you shift out, and we got our serial input as well. Now, what we want to do now is connect a couple of the pins to our XOR. I'll tell you what, let's label these pins. These are all going to be connected to LEDs. So what we can do is we can create LED A, and we'll just edit these. Copy, I'm just pressing C to copy. E to edit. So that's, and you don't have to there's lots of different ways to do this, but this is just how I'm laying it out. So we're not going to, because we don't want to clutter up our diagram, we'll put all those labels there so we don't have to actually wire anything up there. Let's put that in line. So it's in line. Now, so what pins have we got left? We've got a serial input. We've got our Q prime, QH prime, which is the output. Now, what we're going to do is use the XOR. So, Q prime is going to go into one of the inputs of the XOR. And if I remember, so it's XOR in A. So we will create a new label here, L, XOR in A. So the first input to the XOR is going to be that, which means that's the end of all the shifted bits. Now the second pin, we can actually use any of these pins really, of these output pins on this side, to feed into the XOR. But I just arbitrarily decided to use ECD pin E. So pin E. So what we'll do is just move this along a bit, because what we need to do is create a junction here, because we also want this to go to XOR in B. There we go. So that then has both those things connected up. And the only thing left is the serial pin, but what we will do is that's going to XOR. Q prime is going to one of the inputs of the XOR. Pin 4 of the output is going to one of the pins of the XOR, and we're actually going to have this as our XOR output. So our XOR output is going to come back in, feed back in. So this shift register is going to be continually clocked by the 555, and then the output of itself, XORed with the output of one of its pins, will then feed back into the input. So that is the 595 set up. Actually, what I've thought of it, we need a couple of switches. Because when you first start this thing off, what can happen is this will essentially be in a random state. If it happens to be in a random state where all of the outputs are 0, then the XOR of QH prime and pin Q and QE will never be 1. Will never generate a 1, because 2 zeros generate a 0 in XOR, which means that the thing that's fed back into serial will always be a 0, which means we'll have none of our LEDs output. So we want a way to be able to, if that happens, to be able to control it. And it's quite interesting because by being able to control this serial pin, because that's been constantly clocked, we can actually effectively control the seed for this sort of pseudo random number generator. And I want to control it using two things. So one of the things we're going to control it with is we're going to have one output here, and we're going to have one output here. Okay, let's move that along. And then we're going to call this pull high, and we're going to call this one pull low. And I just thought of something, because we do not want this floating around, this pin floating around, we don't want the XOR output floating around either. So what we should do is add a pull down resistor here as well. So I'll add that in there, and so that's going to go to ground, P ground. So what that means is, I'm going to edit that and make that 10K. So whenever there's no input, you know, from when a clock pulse comes along, we want that to be recognized as a zero, logical zero. So by pulling this to ground, we'll make sure that that really is as close to zero as possible. Now, so let's create the two switches. We can add, and I think there is a switch, a push switch. And yeah, so the output of the switch is going to go to, hold on a sec. Okay, just to show this on the picture, you know, we're talking about this bit here, these two switches here. So the pull, we want the output that goes to pull high, to pull the pin high. So we need that to be connected to VCC, which means that when we should probably put a resistor there actually. Otherwise what happens is when you pull it high, you're basically dumping quite a lot of current into there, and it might not be necessary. But I haven't got one on my current diagram, and or on the working prototype, so I'd have to test it out, and I'm not going to stop the video. So let's leave it as it is. It works. So we need another one to pull low, and this will be connected to ground. Now you might be thinking, well, aren't we already pulled down to ground anyway? I'll show you in a sec. You might be thinking, well, hang on a minute, we're already pulled up to ground here anyway. So in the absence of any input, we're going to get a zero anyway. So why do you need a pull low? Well, the thing is, because this thing might be operating, and the output of the XOR output is also coming in here. So we need a way to shunt that XOR output out the way. So we do need actually a stronger resistor than, or weaker resistor than that. Right, that's the two switches. And we could have just put them in there, but we're illustrating the concept of labels by doing that. So the only thing that's missing here is power supply and all of the LEDs. As far as I'm aware, is there anything else wrong? Yeah, actually there is. So I just realised we're actually powering the shift register with the same lower power. So we've actually got a resistor in there that's not VCC. There's just a resistor in there. It's a 480 ohm, 470 ohm resistor. Cool. So now we just got to put the LEDs in. So let's put the LEDs down here. Now we want to add in a LED. And the LED itself is going to have a resistor before it. And the LED is going to be connected to ground on the other side. And we need to give it a label. So it's a little bit laborious. Now I'm going, in my design, I'm going to use a 4.7k resistor. Because I think I can find some LEDs with a higher luminosity output, which will work well with the CR2032. I mean, I've had it running for about an hour now on the desk, and it's still working. But I don't know if it will last the 40 hours. But in any case, you can choose whatever resistor value you want for the LEDs. You can calculate essentially the voltage input at this point from a coin cell, which is nominally supposed to be 3 volts, but mine was producing about 2.8 volts. There was about 1 volt drop across this circuit. So I was getting about 1.8, 1.9. Actually, it seemed to vary depending on the pins. Some of them were 2, some of them were 1.8. But then that means that you need to work out what voltage, given that that's very close to the forward voltage of the LEDs. You can then calculate the current by dividing the voltage drop by the resistance value. Is that correct? Just trying to think if that's correct. Yeah, and then that will give you the current. So let's just copy this. Sorry, that wasn't a very good explanation of working out the resistor values. I need to think about it relative to the whole circuit diagram. Of course, I'm just copying the blocks here. It can be quite. Could they go closer? I wonder. You know, is that? No. Yeah, then go a little bit closer. Okay, where are we? A, B, C, D, E, F, G, H. We need 2 more. Didn't mean to do that. I shouldn't have done that, boss. You shouldn't have done that, man. What the? Sometimes this dragging is a little bit awkward. Okay, that'll do. So then all the LEDs are connected up, and that is actually, I believe, almost everything except a power source. So for now, let's just add a power source. We don't need to add one in, but we will need a component for something like a battery connector or whatever. So if I just add in a pin 1 times 2. Okay. I'm gonna have to go to the browser for this one. I need to see what I'm doing. So under con. Yeah, there we are. 1 times 2. And this is going to act as our power supply. So we have VCC and ground. Now why have I done it? You get to see you can label it like that if you want. But have to forgive my obsessive behaviour. Right, so that's going to be our power connector on the board. And then later on we'll probably change that to a battery or something like that. But I think we're done. I think we're connected up. The only thing we haven't done is specify some of these values. Oh yeah, so on our 555 timer, we're using two 10k resistors. And there's a formula for working this out, which is in the spec sheet somewhere. But essentially we'll have a flash rate of about 2 Hertz, so 2 times a second with that setup, including that resistor. So of course that resistor will count as part of that resistor. Now, okay, so I think that's it. If all of our resistors are done, now what we could do is try doing a design rules, electrical rule check. Okay, yeah, we've got to annotate everything. Let's just annotate everything now then. Give all of these resistors labels. So just click annotate, use the entire schematic, keep existing annotation. The defaults usually work. And now if we look, all of these resistors have now got numbers on them. I can see that we've got a hell of a lot of resistors in there. There's all these lead resistors. So that is the schematic complete, as far as I can tell. If I do a stop it, run the check, there's some errors. So what do these mean? Conflict problem between pins. Did I label these as outputs? How can that be? Why is that a conflict? Or did I not label them as outputs? No, I'm sure I labelled them as outputs, right? Okay, so I think we should try and work through these. Now, if you hear a purring, it's because a cat has just jumped up on my lap. So I just had a look and what this actually means. Now, you're going to get electrical rules checks, and when I first ran this the first time, I was like amazed and thinking, what is going on with all these errors? And actually, you don't even need to do this. If everything's connected up correctly, it doesn't matter. You know, it just does not matter whether or not you have these errors, because it doesn't. It's just for checking. You know, we know we've connected everything up correctly, but maybe we haven't. So I guess in a way, it's good practice to do this. So the first error says conflict problem between pins, severity error. Pin 8, the power out of component U1, which is this ground, is connected to the power out of component U2, which is the ground, right? Now, remember back to the first part of this tutorial, the schematic part. Actually, no, when we were creating library components, we labelled that as a power out, the ground. Now, it's not a power out. I've just had a look on some of the other components, and what they label it as is a power input. So we should be able to get rid of that first error by labelling the ground as a power input. I guess you'd have to look at the reasoning why they call that a power input rather than a power output, and what those things really mean. But in any case, the ground should be a power input. So let's edit that, change it to a, sorry, that's just the browser. Go to the editor. Let's change this to a power input. So normally you wouldn't have this problem, for example, if you were using your designed libraries and so on. They should be right. We'll change it on this one as well. So that's also a power input. Right, so now they're both changed to power inputs, the ground. Let's rerun that check, and obviously we had 10 before, so run it again, and we've still got 10. Somehow. So the next one, pin connected to some other pins but no pin to drive it. Pin 1, power in of component is not driven. Right, okay. These are all still called lead A. I bet someone was watching this when I was doing that was screaming, why are they still all called lead A? That's obviously going to confuse things, isn't it? So let's change these. I mean, it's interesting to see what happens when you do mess these up. And for some reason there's 2 labels on there. Ah, yeah, that was true. So I copied a block here once and I accidentally... I think I copied it twice. So in a way that's quite useful. Because look, that looks a bit strange there. Looks like that has 2 on it as well. So I'm just going to delete those just because I don't want to... What is this? Let me delete all of those. No. Okay, right, there's 5 of them there. Let's copy that block. Now we know we've got 10 of the damn things. We only want 8 of them, so get rid of 2 of them if I can count. Let's just sort this out. Right, now since we've been messing around with everything and deleting things, we need to re-annotate. So just run that again, annotate, yeah, just redoes it. Just say yes for that. Now let's run those checks again. Okay, now there's only 4 errors, so that got rid of most of them. So what is the next one? Okay, so I just looked at this one. Pin 2 of component R29 is not driven, and by the looks of it, yeah, for some reason that's not connected up properly. Not really sure why that did that. Let me just see if that gets rid of it. If I run that again. No, it doesn't seem to like that. Okay, right, so I know what this is now. So this power symbol, for example, here, VCC, or this one here, VCC, doesn't actually indicate that is supplying power. In effect, that's just a label. So what you do is there's something called the power flag, which you can add. Okay, I've just discovered then, I've been trying to work out what these errors are, and I think they're bullshit, basically. Because look, if I go into the design rules check and set the options so that everything is green, because you can change these to either a warning or an error, like if an output's connected to an input or an output's connected to an output. If I select everything as green and press run, I still get that. I still get these errors. Pin connected to some other pins but no pin to drive it. It says that component pin 16 of component U1 is not driven. And it's the same for this one. Because we've made these power inputs, they're obviously connected to VCC. I even tried adding a power flag to say that this connector, this is a power, because obviously a connector isn't a power, but still there's no, we still get the error. So I just think, just forget it. You know, forget it. It's done. Schematic is done. You know, if someone can work that out and tell us you know, how to get rid of that error. I mean, it seems pretty silly, but maybe there's something obvious. Okay, schematic's done. End of tutorial.